We might have just discovered the fifth fundamental force in nature, something that physicists have been hunting for decades. But how do we know an additional force exists in the universe? And why do we really need it in physics? Stay with me. Everything you see in the universe is governed by four known fundamental forces. The first is gravity, due to which the planets go around the sun. It's the weakest force in nature, and it governs the motion of celestial objects. It's all a play of gravity, from colliding galaxies to merging black holes, and from revolving satellites to the orbits of moons and planets. The second is the electromagnetic force that governs the motion of an electron around the atomic nucleus. Not only that, but the electromagnetic force is also the force that directs the behavior of light. In fact, light is nothing but an electromagnetic wave propagating through space. The third is the weak nuclear force that is responsible for the radioactive decay of the atoms. And finally, we have the strong nuclear force that binds the protons and neutrons together inside the nucleus. As the name suggests, it is the most potent force of nature. So far, so good. Now, to understand the origin of a new force, we need to go back to the 1950s. It was the era of particle discoveries. Each year, several new particles were being discovered. There was a joke among physicists that the year's Nobel Prize must go to someone who does not find any new particle. Because of discoveries, experimentalists were happy, but the theoretical physicists were drowning in the soup of new particles. So they had to develop an acceptable theory that classifies and explains the particles, and most importantly, predicts the existence of new ones. It took more than a decade to formulate such a theory. That theory is the Standard Model of Physics, unification of three of the four fundamental forces. Gravity is not part of it. Einstein's general theory of relativity better defines gravity. Understanding the Standard Model is vital to understanding the so-called fifth fundamental force. The Standard Model table contains four categories of particles. The first is the family of 6 quarks, the elementary particles that make up hadrons, such as protons and neutrons. Next, we have 6 leptons, electron, muon, tau, and the 3 neutrinos. Then we have the 4 gauge bosons, or the force carriers, photon, gluon, W, and Z. Finally, we have the Higgs boson, the last missing piece of the Standard Model discovered in the previous decade. The Standard Model of Physics, although a masterpiece in itself, is incomplete. For example, it does not unify gravity with other forces, and doesn't speak of dark matter and dark energy that make up about 96% of the observable universe. That's why physicists have been looking for a new force in nature for decades. One place to find this fundamental force is in the family of quarks by studying the decay of the beauty quark. It's an unstable particle and lives for just 1.5 trillionths of a second before decaying into other particles. When a beauty quark decays, it transforms into a set of lighter particles, such as electrons, through the influence of the weak force. So one of the ways a new force of nature might make itself known to us is by subtly changing how often beauty quarks decay into different types of particles. According to the Standard Model, a beauty quark should not discriminate between an electron and a muon while decaying. A muon is a carbon copy of an electron, except that it is 200 times heavier. The rate at which the beauty quark decays into a muon must be equal to the electron. But in March 2021, the researchers found that the muon decay was only happening about 85% as often as the electron decay. Nature seems to be preferring one decay channel over the other, a violation of the law of lepton universality. While it was exciting to see this anomaly, there was a 1 in 1,000 chance that the result was a statistical fluke, down to a random statistical wobble. Physicists call this value 3 sigma. 1 in 1,000 may not sound like a lot, but to be really sure about discovery or observation, we need to get to 5 sigma, corresponding to less than 1 in a million chance of the effect being down to a statistical fluke. Researchers now analyze more data from the LHCb experiment. The B in LHCb stands for beauty. However, scientists never actually study beauty quark decays directly, since all quarks are bound together to make larger particles. The March study looked at beauty quarks that were paired up with up quarks. The new results studied 2 decays, one where the beauty quarks were paired with down quarks, and another where they were also paired with up quarks. The fact that the pairing is different should not matter because the decay going on deep down is the same. Scientists expect to see the same effect if there is a new force out there, which is precisely what they saw. This time, muon decays were only happening around 70% as often as the electron decays, but with a large error, meaning that the result is about 2 sigma from the standard model, around a 2 in 100 chance of being a statistical anomaly. Although not accurate enough to be firm evidence of a new force, this shows that the new study aligns perfectly with the previous result and supports the idea that we might be on the brink of a significant breakthrough. Meanwhile, other experiments at the LHC and the Belle 2 experiment in Japan are closing in on the same measurements. It's exciting because this study might open a new window to the most fundamental ingredients of the universe.